All right, so in this video, we're going to take a look at an example of decomposing this acceleration vector. In particular, we're going to find the unit tangent, unit normal, the scalar a sub t, and the scalar a sub n. And so I've summarized the formulas from the last video, and I just wanted to explain that the way I do this is different than what's described in the text a little bit. I find that since the description I gave in the last video was generally pretty straightforward, that sticking to this approach will continue to make it a little easier to understand without needing a bunch of unnecessary things. So just something to keep in mind as we move on. So as you take a look at what we're trying to find and the formulas that we've now derived to come up with that, we'll go ahead and get started here. And one of the big things that we'll clearly need are going to be the v's and the a's. And so we'll start here with r prime of t, which is also going to be equal to v of t. And so we're going to get a 1, a t, and a t squared when I take the derivative coming through here. Okay? So then v of 1 is going to be 1, 1, 1. All right, so I'm going to hang on to that for just a second. R double prime of t is going to equal v prime of t, which equals a of t, okay? And so if I take the derivative now up here of this guy, that's going to give me a 0, a 1, and a 2t. So 0, 1, and a 2t. Now, my a of 1 is going to be 0, 1, 2. All right, so I've got my v, I've got my a. Tell you what, let me box those in so I can find them a little faster here in a minute. There's my v, there's my acceleration vector. I'll additionally need the magnitude of v, so I guess now's as good a time as any to hit that. So the magnitude of v, that's going to be the square root of this thing squared plus this thing squared plus this thing squared. So that just gives us the square root of 3. You guys have found a lot of magnitudes by now. No doubt you can follow that. All right, so let's go ahead and start with a sub n. And for a sub n, we'll need this cross product, okay? So I'm going to start with a sub n and that cross product of v cross a. So that's going to have our I, j, k on top, and then I'll have my 1, 1, 1, and 0, 1, 2 from the vectors v of 1 and a of 1. And so when you do this cross product, you'll get a 1, a negative 2, and a 1. Okay, we'll then need to find the magnitude of that. So we'll find the magnitude of this, which, again, if you come through here and take this thing squared plus this thing squared plus this thing squared and we square root it, that's going to give us a square root of 6. So what we have so far is this guy right here. I'll need to now divide it by the magnitude of v. So I'm going to divide that by the square root of 3, which equals the square root of 2. So that's going to be our a sub n. I'll box that in as well. All right, so then for a sub t, that's going to be where we need to find the dot product of this vector and this vector. So if I dot 1, 1, 1 with 0, 1, 2, I'm going to get a 3 out of that. And once again, dividing by the magnitude of v, that's going to be divided by the square root of 3, which equals the square root of 3. So there's our a sub t. All right, so thus far we've found a few of the things that we need. I'm going to try to make this screen a little easier to see so I can write, continue writing down. We have found so far a sub n and a sub t. So the next thing that I would recommend finding is the unit tangent, okay? The unit tangent is going to be the first step in finding the unit normal, and we know that finding that unit normal is pretty tough. So we're gonna start with that unit tangent, okay? So in terms of finding that unit tangent, we've done these before as well. That's going to be where we take this velocity vector right here and divide it by its magnitude. So that's going to be 1, 1, 1 divided by the square root of 3. Conveniently, we have all of these numbers and vectors available to us already, which is going to give us then for the unit tangent 1 over root 3 1 over root 3, and 1 over root 3. All right, so that's a good place to be as well. Now, when it comes to the unit normal, I found the easiest way to do this is actually just kind of reverse engineer it, okay? So what I mean by that is, if I take this thing right here, and I already know this guy, I already know this guy, I already know this, and I actually already know A, right? A sitting right here. I can solve this equation algebraically for vector, the unit normal vector, and then I've kind of walked my way into it. So let me go ahead and do that. So if I take this thing right here and I solve it for the unit normal, I'd find out that that unit normal is going to be A minus A sub t times the unit tangent divided by A sub n. And remember, I have all of those other missing things. So n is going to be our acceleration vector. So we've got 0, 1, 2, 0, 1, 2, minus A sub t, which was the square root of 3, times the unit tangent, which is 1 over root 3, 1 over root 3, 1 over root 3, all divided by A sub n, which was the square root of 2. And so a little bit of vector arithmetic here, and we would find out that our unit normal is going to be negative 1 over root 2, 0, and 1 over root 2. And so I found that, generally speaking, that's a more efficient way to come up with that last missing component of what we were trying to find up here to begin with. All right, so the next thing we're going to talk about is the Tnb frame. Now, the Tnb frame, the T, the N, the B stand for 3 different vectors. T stands for the unit tangent, N stands for the unit normal, and then B actually stands for the binormal vector. So let's suppose we have this setup right here, where these are all vectors, and this is our unit tangent, and this is our unit normal. Then the vector that's perpendicular to both the unit tangent and the unit normal would be this B vector, which is the binormal vector. So binormal vector. And again, the binormal vector is going to now equal the cross product of the unit tangent and the unit normal. Okay? So this frame that we see right here actually has 3 important planes that we discuss. We've got this plane right here, this plane right here, and this plane right here, and they all have names. The first one that I'll mention is the osculating plane. So that would be the osculating plane made by the unit normal and the unit tangent. The plane made by the unit normal and binormal will be the normal plane. And then the plane made by the unit tangent and binormal vector would be the rectifying plane. Rectifying plane. Okay, so we'll take a look at finding the previous example and then finding the equation of one of these planes as well. But for right now, really all you need to know are the names, and then that this new binormal vector here is a result of the cross product between the unit tangent and the unit normal. All right, so the example that I've added to the screen is the same example from the previous problem. We're going to have this vector here at t equals 1, and we're going to find the osculating plane, okay? So the osculating plane would be this guy. And if you remember, to come up with the equation of a plane, we need 2 things. We need a point, and we need a normal vector. Well, the point's going to be pretty easy to find. The point is going to be found by taking t equals 1 and plugging it in here. So when I do that, that's going to give me the point 1, 1/2, 1/3. Now, the normal vector that we need is actually going to be the binormal vector. If this is the osculating plane, the vector that's going to be normal to it would be this binormal vector. The binormal vector is going to be the unit tangent crossed with the unit normal. I've picked this problem because we've already got these 2 things. We found these in the previous problem. So let me go ahead and write that down. That's going to be the I, the J, and the K. And from the previous problem, the unit tangent was 1 over root 3, 1 over root 3, 1 over root 3. The unit normal was negative 1 over root 2, 0, positive 1 over root 2. And when you cross that, you end up with the vector 1 over root 6, negative 2 over root 6, and 1 over root 6. So we've got our point, we've got our normal vector. Therefore, it's a matter of just putting it together as we would have in the previous chapter. So we're going to have 1 over root 6 times x minus 1 minus 2 over root 6 times y minus 1/2, and then plus 1 over root 6 times z minus 1/3 set equal to 0. So this would be the equation of the osculating plane for that last example. And just as kind of a recap there, remember these are the components of the normal vector, this guy, and this guy, followed by the point x, y, and z from right here. Okay, the normal plane and the rectifying plane, you could find those pretty similarly. When a problem like this, and you'll see this on the quiz, in a problem like this, it's not necessarily finding the actual plane itself that's hard. As you can see, it's finding all of the additional things that you would need leading up to it, like we did in the last problem.